Hi, welcome to section 16.2. I think this is a really cool section. It has nice geometric applications and it has some pretty precise formulas to be able to work with. So people who are into geometry and people who are into algebra are going to like this section, I think. So we're going to talk about line integrals, and there are just two different types of line integrals that we'll cover. Today's goals are to be able to compute scalar line integrals and describe them geometrically, and also to be able to compute vector line integrals and describe them geometrically. It's only two goals, but actually I guess that's four goals all compressed into one, and hopefully I don't get too sidetracked into theory, because I really do like talking about the theory behind the geometry. So before we get started, I want to do just a brief recall of paths, because it's been a little while since we talked about a path. So recall, let's say that I have a path. C of t is going to be some function x of t, y of t. Typically, for this discussion right now, we're going to talk about paths that just have outputs in R2. And I'm going to represent that by some squiggly line. It means that for some given time t, let's say at t equals 0, I get an output that's a point right here, and maybe at t equals 5, I get an output right here. And as t changes, it's going to trace out some path here in the xy plane. That's what my path does. I put in an input that's t, and my output is going to be some point along this curve. And remember, one of the tricky things about paths is that they can have variable speeds. So as t changes, and maybe I'll have a little grid here to keep track of my t values. My t values are going to go from, I shouldn't write that up here, my t equals 0, my t equals 5. If I break t up into equally spaced increments, that doesn't necessarily correspond to equally spaced increments along this line. That maybe at t equals 1, I made it all the way to here, and then I have little tiny baby steps, t equals 3, and then maybe t equals 4 is somewhere right around there. Right? So as I break up t into little increments, that might not necessarily correspond with breaking up this line into evenly spaced increments. This is the basis that we need to start talking about scalar line integrals. So for a scalar line integral, I need two different pieces. We have a path, and typically that path is going to be represented by a path down here in the xy plane, so it's flat, just like we had in our previous example. We also have a multivariable function, f of xy, and I like to represent our multivariable functions by these magic carpets, right? So here's my magic carpet, my f of xy function, and here's some path that I have down in the xy plane. I'll call this path c of t. What is a line integral geometrically? So geometrically, our scalar line integral, we're going to compute the height of the function along this path. Height of the function along the path. So hopefully that's a pretty intuitive concept. The idea is that for every point along this path, it's going to map up to some point that lives up here on this magic carpet, right? And as the magic carpet gets taller and shorter, those are going to, whoops, that doesn't line up at all. Sorry. I'm going to block the view for a second to make this line up a little better. Maybe this carpet didn't do such a good job of getting taller and shorter, but as the carpet gets taller and shorter, it means that this line integral is measuring this whole area. It's the area where the base is given by the length of the curve, and the height is given by the height of the function. So I don't just want the height of the function along the path. I actually maybe want the area where the base is given by the length of the curve, the length of c of t, and the height is f of xy. So if I were to estimate this using rectangles, I could break this path up into little pieces, and then for each of these little pieces, I could estimate the height, and I could do something similar to a Riemann sum, right? It's sort of like a three-dimensional Riemann sum. Oh, those rectangles look sort of wonky, but you get the idea that I have all these flat rectangles. It's not a volume, it's just the area of this sheet, with the base of the sheet curving along the path, and the height of the sheet being the height of the function. That's all of the hard theory that I want us to get to. But the hard part is, how do I convert this idea into a computational integral, something that I can compute, right? And it turns out that we have this nice formula. And I'll just skip to the formula, and then I'll explain where this formula is coming from. So our formula, typically our notation for our path notation, our book uses something that's, well, I don't know. We say the path integral along my path C of my function f of xy ds, because it's given in terms of the length of c of t, and we usually use s to denote length. This is going to be the integral of f of c of t. So I'm going to take my function and I'm going to plug in the points along this path. F of c of t really is this blue curve here. It's giving me the height. Times something that you might not expect. This is the height, we want to multiply it by the length, right? Well, what's the length of that path? It's c prime of t dt. Am I off camera? No, I've got plenty of space, great. So the length of base, and you might be having some like traumatic flashback experience right now, because the last time we saw something like the magnitude of c prime of t, it was back in chapter 13, and maybe you didn't really like chapter 13 and you sort of want to put all that behind you, but really this is a really easy formula to work with, and I think it's very intuitive. So I'm going to take 2 minutes to explain why I think this is very intuitive. The idea is we can't parameterize our path with respect to s typically. Typically our paths have variable speeds. If we had a speed of 1, then this would be 1 and we wouldn't have to worry about it. But typically we don't. Typically we have to take into account that we could move really fast along certain parts and really slow along other parts. So remaking this picture, given the fact that I have variable speeds as I go along here, it means that when I break t up into evenly spaced intervals, that's what my dt does, right? I'm breaking my t up into these evenly spaced intervals. It means that some of my rectangles have really long bases, and some of my rectangles might have really short bases, right? So visually, that's sort of the idea behind what's going on. And when I say, what is the magnitude of c prime of t? Well, c prime of t, if you recall, we talked about that in terms of the velocity. And so this is the speed. And I'm saying that I'm taking into account the fact that I'm traveling further for certain rectangular bases than I am for other rectangular bases. That's sort of an intuitive concept behind it. Another thing to recall, and I'll write this down, recall the length of my path c of t is given by the integral as t goes from a to b of the magnitude of c prime of t dt. If there's one formula that you remember from chapter 13, this is one that I want you to think of. That the length of c of t is going to be the speed, that's what this is representing, the speed, and then you're adding up that speed along all of these different times. And if you know how fast you're going and you know how long you're going, then this should give you a distance. And we call this the arc length, the length that you've traveled. And notice where those pieces are exactly in this formula, that when for my line integral, I want to measure the length of the path and the heights along that path. That's exactly what this integration is doing. For each incremental value of t, the length of the base is given by this. That's what my arc length is. And then I'm adding up all of those arc lengths, multiplying by the height at each place. So that's all the theory that I want to talk about. And this is the function you'll write down in your notes. But I do want you to be able to tell me, what does this chunk represent? It represents the height. And what does this other chunk represent? It comes from the fact that the distance, the length of my path C of t is given by this distance function, this arc length function. So let's put this into action, and we're going to do an example. Let's say that I have my magic carpet function. The height is given by 10 minus 2x minus 5y. And my path in this case is given by C of t equals t, comma, 2 minus t. And my t values are going from 0 to 2. The first thing that I want to do is get an idea of what's going on with my path. So I see that when t equals 0, I get that C of 0 is equal to 0, 2. So that's 0, 2. And then my other endpoint, when t equals 2, maybe I shouldn't label this. So when t equals 2, I get an output of 2, 0. 2, 0. And it turns out, oops, this is 2, 0, and this is 0, 2. So my path is actually just a straight line. Another way that I know that this is a straight line is I could convert this path. Maybe this is something you don't want to think about, but I know that my x component is equal to t, and my y component is equal to 2 minus t. And I can see by substitution, if x is equal to t, it means that y is equal to 2 minus x. So I have a y-intercept of 2, and it's a slope of -1, and I get this path. So the first thing that I did, I looked at what the path looks like. And we know for our line integral, I'll write it down now and I'll write it down again, the line integrals for scalar valued functions, they're going to be the integral from t equals the bounds on t, which in this case is 0 to 2, of f of x, y, times the magnitude of c prime of t dt. So in order to compute this, I'm going to do a little bit of pre-work, and I'm going to find out what is the magnitude of c prime of t, or what is the speed in this case. That's my conceptualization. So c prime of t is given by the derivative of t, which is 1, and the derivative of 2 minus t is just -1. So if I want to know what is, and this is a special case that these are linear functions. Sometimes I might have functions of t in here. That's okay though, and we'll see other examples of that later. What is the magnitude of c prime of t? It's going to be each of these terms squared. So I have 1 squared plus -1 squared, all square rooted, which is equal to the square root of 2. And notice that we have a constant speed in this case. It's a simple example. That means that as I travel along this line, my delta t's are going to correspond with some delta s's. That as I elapse 1 unit of time, that change in time is going to correspond with equal units of change in distance. So now I found this piece. I'm going to plug that into my formula. I'm also going to plug my function into the formula. And I'm going to compute the integral. So we have 10 minus 2x minus 5y, all times the square root of 2. That's the magnitude of c prime of t dt. Oh, wait. Something's wrong in our formula. I sort of intentionally made this mistake because this doesn't work. I have x's here and y's here, but I have to take my derivative with respect to t. It's because before I can plug in f of x, y, really what I want to plug into this function is f of c of t. I want to be able to evaluate this function along this path. So I'm not taking every single x and y everywhere. I only want to know the x's and y's that correspond with these particular relationships of t values. So what does that look like? In this case, I already erased it. We already know that x is exactly equal to t. Maybe I'll, I don't want this to be confusing. I'm looking at my path function, and in my path function I see that x was equal to t, and y was equal to 2 minus t. So that way, if I want to know what is f of c of t, I'm going to plug in t for my x value, and I get 10 minus 2 times t, minus, and I'm going to plug in 2 minus t for my y value, 5 times 2 minus t. And now I can do a little bit of algebraic simplification. 10 minus 2t minus 10 plus 5t. I get the plus 10 and the minus 10 canceling one another, and I get just the function 3t. So it means that my final integral is going to be an integral from t equals 0 to 2, because those are the bounds on t, of my f of c of t function, which is just 3t, times the magnitude of c prime of t, which we already calculated to be the square root of 2, dt. These are just constants, and so when I integrate with respect to t, I end up with 1/2 t squared times 3 times square root 2, all evaluated from t equals 0 to 2, and I can plug in those values, and I end up with 2 squared is 4, divided by 2 is 2, so I get 6 times the square root of 2. When I plug in 0, I get 0, and this is my solution. 6 times the square root of 2. Well, what does that actually mean geometrically? I'm going to go back and describe geometrically what's going on with the same picture that we saw before. So rather than writing our path in the xy plane, I'm now going to write it in 3 dimensions. So this is what my path looks like. And then on top of this, I have some function. And in this case, my function is a plane. I chose an easy function. It has a z-intercept up here at 10. It has a y-intercept when y is equal to 2. And it has an x-intercept when x is equal to 5. So this is a sketch of the corners of this plane. And I'm taking the path that doesn't quite line up with the corners of the plane. It lines up at this point right here, which is the point 0, 2, 0. And what does this line integral measure? It's measuring the height of this plane along this path. So if I were to draw sort of the little heights that come up and hit this triangle, it's measuring the area of that.